Okay, so we should get started. So next up, we're very happy to have Austin Joyce from Chicago to tell us about differential equations and cosmological correlators. So please.
Great, thanks. Yeah, so first of all, let me thank the organizers for putting on such a nice meeting and for giving me the opportunity to talk. It's really wonderful to be here. And I'm also quite pleased that there's like a nice representation of cosmology in the program. I hope that that is reflecting the interests of the community and not just the interests of the organizers. But if it's the latter, hopefully I can convince you to be interested. So as you can see from the title, this talk is going to have something to do with cosmological correlators, something to do with differential equations. I'll try to tell you how these two things are related. So Enrico gave a beautiful introduction to why we should care about cosmology. But I always find, I also need to like psych myself up for these kinds of talks. So let's sort of revisit why you should care about cosmology. So here I think many of us are interested in fundamental physics. And so if you're interested in fundamental physics, why should you care about cosmology? So a zeroth order thing that we know is that the universe is expanding. And so with a fixed amount of stuff, if I put it in a box, I make the box bigger, the density in the box is going to go down. But if I go back in time, the density is getting higher and the temperature is getting larger. And so the very early universe was much hotter and denser than the universe today. And if I really take this extremely seriously and just play the movie all the way back in time, at some point I stop knowing even what to do, right? The laws that I'm trying to use to describe the physics don't make any sense. And in particular, possibly even the concept of having a space-time at all stops to make sense. And so that indicates that if you're interested in understanding sort of the breakdown of fundamental laws, this is an interesting place to be. And so as Enrico beautifully told us, the window that we have onto the very early universe is through measuring the statistical distribution of matter in the late universe. So fundamentally, in cosmology, the things we measure is the distribution of matter and the correlations between the distribution of objects. We don't care so much that there's a galaxy in any particular direction in the sky. What we care about is the statistical correlations between these objects, okay? And what we do in galaxy surveys, cosmic microwave background measurements, et cetera, is we trace the evolution of these correlations through cosmic time, and by doing that, we infer both the dynamics of the universe and what's in it. Okay, and one thing I want to emphasize is that we have a putative origin story for the correlations that we see in the late universe that we call cosmological inflation. So as Enrico said, this is a pre-hot Big Bang evolutionary phase of the universe, where we think that the correlations that we see in the late universe were seeded as quantum mechanical fluctuations. To me, this is one of the most beautiful stories in science. It's really a striking thing that what we really see writ large on the cosmic universe is quantum mechanics. But what that means is that if we're really interested in understanding fundamental physics, early universe, breakdown of space-time, whatever, what we need to do is we need to grapple with quantum correlations in cosmological spacetimes. And of course, this is the domain of quantum field theory. So this tells us that studying quantum field theory in cosmological spacetimes is going to be an interesting thing to do. So that's what we're going to talk a bit about. And luckily for me, you all have made a lot of progress in studying quantum field theory in the last, I don't know, N years, mostly in the context of flat space, but including many cases with dynamical gravity. And one way of saying what the goal of me and my friends is we want to understand or develop a similar understanding of quantum field theory in cosmological spacetimes. And we want to do it for, roughly speaking, the reasons that I told you. Okay, so we want to import some of these insights from sort of flat space, some of the tools of, say, the amplitudes program into the cosmological set. Okay, so I won't have time to tell you about all of the things that we are starting to figure out. Enrico reviewed many of them. I think others will tell you some other things. But if you want a sort of zeroth order summary of some of the state of the art, some of the ways of computing these objects, Daniel and I are very slowly, I'm mostly the bottleneck, trying to write some lecture notes on these types of things. So here, if you scan this QR code, you can see the current state of the work in progress. If you find mistakes, please let us know, and other comments are also more than welcome. Okay, so first I'm just going to say a few brief things about the objects that we want to compute in cosmology. Then I'll tell you a little bit, this idea of differential equations will actually enter the story in the second part of the talk. And I'll try to give you some idea of what this sort of bootstrap-like philosophy is or could mean in cosmology. And then I'll conclude with some help. Okay, so let's start with cosmological correlation. Okay, so importantly, we don't actually directly see the inflationary epoch. Instead, what we do is we actually infer its presence by measuring correlations generated by inflation at the sort of space-like boundary at the end of inflation that we call the reheating surface. This is a future boundary of the inflationary spacetime. And what we do from the pattern of correlations is we infer the physics of the inflationary universe, right? So properties like the locality of interactions, causality, unitarity, the symmetries of the spacetime, what kind of stuff was propagating the spacetime, are all encoded in the statistics of correlations that we measure at the end of inflation in some non-trivial. Okay, so the standard way to do this, so this, as I told you, is a problem of quantum field theory and cosmology. And so there's, of course, a Feynman diagrammatic way of thinking about this problem. And in fact, that's the usual way that we proceed. Okay. So what we want to do is we want to understand the correlations generated by inflation on some late time slice. And as a matter of principle, we can assemble those things by summing over Feynman diagrams. Okay, and as a matter of practice, the thing that I'm going to be interested in, the way I'm going to capture the information about cosmological correlations, is in just the state of the universe at the end of inflation. Or in this talk, gravity is going to be fixed, so it's going to be the state of a quantum field theory on the late time surface in some cosmological spacetime. And for me, I tend to like to capture this information using a representation of the state directly. And so I like to really represent the state in the basis of, let's say, field eigenstates. And so the thing I'm actually interested in computing is like the wave function of the system on some late time surface in a cosmological spacetime. This is sort of like a pre-observable. It has a similar ontology to the S matrix in the sense that if you want to turn it into an actual observable, you have to square it and integrate it. Here, the thing you should do is you should take psi star psi. That gives me a probability distribution. I multiply by the sort of field operators that I'm interested in, or the field values that I want to correlate. And then the result of this now path integral will give me this thing that I will call an in correlator. So I guess I learned that maybe I should be a little bit careful about that. Okay. And so as a practical matter, this is the thing I want to compute. Okay, and so it ends up being very convenient to parameterize the wave functional in the basis of field eigenstates in this exponential way, right? So this is a bit tied to perturbation theory, but everyone here, I think, I don't really have to sell perturbation theory super hard, so this is a pretty good representation of the state for our purposes. Okay, and as you see, when I expand this, there are these various kernels that appear in the wave function. And these kernels are the things that actually capture the information about the way that fields are correlated, right? They're capturing the statistics of correlations in this state at late times. And so those are really the things that carry the information that I'm most interested in. So those are kind of the things I'm going to directly compute. Okay. And for kind of obvious reasons, I will call these things wave function coefficients. And luckily for me, there is a nice Feynman diagram expansion that can calculate these things. Okay, and of course, the physics of whatever generated them is encoded in their properties. I should probably make a note on kinematics, just because the kinematics in cosmology are, of course, slightly different from scattering amplitudes. So as a practical matter, we're interested in the correlations of a system, typically at some instant in time. Of course, you can also consider unequal time correlation functions, but in this talk, I'm only going to be interested in equal time correlation functions. And so fundamentally, the sort of strength of correlations, at least in perturbation theory, is a function of, or at least, let's say the moments of the probability distribution depend upon the points that I'm choosing to correlate. So if I want to look at n operators, there will be n points at an instant in time that I'm interested in correlating. And in cosmology, we believe, or we have very good evidence, that the universe is at least statistically homogeneous. And so we tend to like to go to Fourier space. And so we think of the fundamental kinematic variables that correlations depend on as being a set of wave vectors in Fourier space. Okay, so we're going to imagine Fourier transforming this configuration of points to a bunch of 3 momenta. So here I'll always be in 3 plus 1 space-time dimensions. And because of the translation invariance of the system, these 3 momenta will form some closed shape. Okay. Importantly in cosmology, cosmology, as I told you at the beginning, depends on time. So that time dependence tells us that energy is not conserved. And so in contrast to flat space scattering, cosmological processes or correlations can depend upon the energies involved in the process. And so, strictly speaking, the kinematic variables that cosmological objects depend on is more than in flat space, or at least in scattering amplitudes. And at the level of sort of this like kinematic polygon, what it tells us is that correlations can depend upon the shape of this polygon and the lengths of the sides. That's sort of the analog of energy in this setting. Okay, and I will often abuse terminology and call this length in energy, despite the fact that there's sort of it's not a conserved quantity necessarily. Okay. Very good. Okay, so why is this hard? Why don't I just do it? I mean, why am I like telling you that we need your help, whatever? And the problem is, in cosmology, precisely because things depend on time, I need to integrate over all possible times at which various processes can take place. So for example, if I wanted to compute this kind of simple exchange process, I imagine that I have 2 particles exchanging an intermediate particle with 2 other particles. There are sort of many different instants in time at which the interactions can take place. And because the physics is not time translation invariant, I have to actually literally sum over all the possible ways that this can happen. Okay, so I'm forced to do some sort of time integral over the locations of these interaction vertices. And in the most generic case, this type of simple looking, like 2-to-2 single exchange process is related to this kind of integral. Okay, so it's some nested time integral of a whole bunch of Hankel functions. As was pointed out, we do know many things about Hankel functions, but here if you try to do this integral, the types of things that pop out are like Compé de Fourier functions, like multivariable hypergeometric functions, stuff like that. They're things which are basically just names, and the properties of the functions are not particularly well known. That said, if you do know how to do this integral in some nice way, please come tell me. But as a practical matter, doing integrals like this is like, it's not super easy, or maybe someone will tell me it is. But when you start to get to formulas like this, you start to think, okay, maybe I'm not totally organizing the calculation in the most efficient way. Maybe there's a better way of thinking about things. So we're gonna try to at least start to make progress towards a better way. Okay, so philosophically, one reason you might think there's a better way is quite similar to the S matrix, that there's a whole lot of extra baggage that we've introduced in this calculation, right? The thing I actually care about, I care about the correlation function, like as a function of the kinematics on this late time surface. I don't actually care about the time evolution per se that gave rise to it, except in as much as it's encoded in the actual final object, right? So I'm only kind of inferring that there even was any time evolution here. So it's a redundancy, if you like, that I've introduced in order to integrate over and get out the final observable object. Okay, so you might just ask, can we like get rid of the bulk time evolution and directly reconstruct the observable output? So that's this, philosophically, that's what this cosmological bootstrap is about. Okay, of course you could say, we'll come back. Okay, so let me try to tell you a little bit more in detail some of the techniques that we have been using. Okay, so ultimately, as Enrico told you, the thing we actually care about is the fluctuations of the matter distribution or possibly gravitons in the late universe. But that's quite complicated, and we want to try to start to get some handle on the underlying structure. And so in many cases, in physics, it's useful to simplify the problem in order to get further, and then you try to abstract the lessons from this simplified setting to the thing you actually go out and measure. So here I'm going to simplify the problem to the point where I can kind of imagine solving everything, and then we'll try to export those techniques back to the more physically realistic setting. Okay, so what I'm going to do is I'm going to simplify the problem by fixing the background to be totally rigid. I'm going to consider just a fixed FLRW spacetime with some power law scale factor of this form. And I'm going to populate it with a very simple theory, just a conformally coupled scalar, so it has this special conformal coupling, with only a cubic interaction, though of course, considering other polynomial interactions, or even derivatives doesn't change the story so much. Okay, the reason that I did this is that I can now Weyl transform this action to make this scalar feel as though it lives on flat space. But the price that I pay is now the theory has some kind of time-dependent coupling. So the sort of impact of the non-trivial cosmological background in this setting is that it looks like a time-dependent quantum field theory on flat space, where the time dependence is this precise thing fixed by the cosmology. Okay. So as a practical matter, it's useful to deal with this time dependence by kind of going to frequency space. So I imagine I decompose the time dependence of the coupling into Fourier modes. And then that will simplify my life, and then I'll kind of reintegrate over all the Fourier modes at the end. Okay. So doing this, I can now write down sort of a complete set of Feynman rules for this very simple theory. And what I'm wanting to compute is I'm going to want to compute the wave functional on some time slice. So this is kind of a Dirichlet boundary value problem. I want the wave functional as a function of some field profile at late times. And so it means that the perturbative objects that I introduce in order to do this calculation are slightly different from the ones that I would use to compute a scattering amplitude. And in particular, there are kind of two types of lines now. So there's sort of lines that make their way out to the late time slice, which I just associate with kind of free plane wave propagation. So this is the analog of like a bulk to boundary propagator in ADS CFD. For internal lines that connect two vertices, I use kind of an analog of the Feynman propagator, but it has this peculiar, well, not so peculiar additional piece that ensures that the right boundary conditions are met order by order perturbation theory. And then here, the kind of interesting thing about cosmology enters at these vertex factors. So since I've gone to Fourier space, I get a factor of omega to the epsilon and something that also looks like a plane wave. So the cosmology dependence shifts the energy flowing out from this vertex to the boundary. And then at the end, much like in the ordinary case, I have to integrate over all possible locations where the interaction can take place, and then I have to integrate over all of the energies associated to this coupling. So the whole reason for thinking about the problem in this way is it tells me that at least in this particular model, the FRW wave function can be expressed as sort of an energy integral of the flat space wave function, right? So I want to do integrals of this type. So this is a very nice setting where cosmology sort of just corresponds to integrating the flat space object. So that's another reason to like this simplified setting. In general, it will not be quite so simple. Okay. So here, now that I know that kind of the flat space wave function is playing the role of an integrand, it kind of makes sense to try to learn something about the flat space wave function to start. And in particular, we should compute it in some settings, stare at it, see what its properties are, and things. Okay, luckily, it's pretty easy to count. Okay. All right, so let me just give you like 2 examples, and then I'll show you how to generate all possible examples yourself. You can go home and play with it. So the simplest example, so this is a theory with like a phi cubed interaction, so we should compute the 3-point wave function coefficient. And here, it just corresponds to this exponential integral. So I integrate from -infinity up to 0. And the final answer only depends on the sum of the energies of each of these lines, which I'm going to call like capital K in red. And the wave function is the simplest possible thing. It's just 1 divided by the total energy flowing out to the boundary. Okay, so that, not super exciting. And here I should say I've set the coupling constant to 1, but of course it can be. Okay, not super exciting, but still has some interesting features already. Maybe the first kind of non-trivial thing where you have to do an interesting integral is to compute this sort of exchange 4-point function. So this now has two interaction vertices. You have to be careful about their relative time ordering, things like that. So here I've kind of suppressed the contributions. There are three different contributions because of the two time orderings of the Feynman propagator and the untime ordered piece. The thing which is nice, and it's like the first hint that something interesting is happening, is that you've computed three things, and they're all like a little bit messy. They're not super nice. But when you add them up, you get something really simple and nice. Okay. So we can stare at this for a little bit. So you see it has kind of three factors. And the three factors are kind of naturally related to the total energy in this diagram that makes it out to the boundary, kind of the energy associated to the left vertex and the right vertex. And here, these K1, 2 just means the sum of K1 plus K2. Yes? That's correct, yeah. It is important. It will play no role in this talk, but I'm happy to, yeah, it is important. As a practical matter, you can ask, how did I actually do these integrals? So I imagine that the I epsilon is such that the integrals converge in the past. Okay, so it killed the contribution. But yeah, that's kind of a long story. I think it's understood, but. Okay. Very good. Okay, so this is already a slightly interesting rational function. Okay, and if you try to look at the next most complicated thing, like a 5-point function with 2 exchanges and stuff like that, the number of terms you have to calculate start to proliferate. So the 5-point function involves 10 different time orderings. You can do it, it's no big deal. But there's a simpler way to proceed that allows you to just generate all of these integrands and start to explore their structure. And one thing that's nice about it is it's a bit more in the amplitudes world. It's some kind of combinatorial definition or combinatorial construction. And it turns out that you can reproduce the output of all of these time integrals from what I'll call graph tubings, which are really just ways of circling the Feynman diagram. So imagine I want to compute some Feynman diagram here. Yeah, sorry, this should only have one leg in the middle, I guess. But imagine this is some Feynman diagram with like n exchanges. Doesn't really matter. The first thing I can do is I can kind of truncate this graph because it doesn't actually depend directly on any of the individual energies of these lines that make it out to the late time surface, but it only depends upon the sum of energy flowing out of a vertex. And so it becomes useful to kind of label this graph by the energies associated to each of its vertices. Okay? So now given this kind of truncated graph, what I'm going to do is I'm going to imagine all possible ways of encircling all of its vertices with as many circles as possible, with the only rule is the circles cannot overlap. Okay? Once I've done that, I catalog the energy flowing out of all of the circles, and then I take 1 divided by the product of all of those energies, sum over all possible ways of maximally circling the graph, and I claim that is the wave function. So let me give you some examples, and then you'll understand it all. Okay, so the simplest one is this 3-point function, which has kind of a single node. So flowing out, so here I'm kind of implicitly including these lines that flow out to the boundary just so we can orient ourselves. So you imagine circling this single vertex, and through this red circle, 3 lines pierce this circle. They have energies K1, K2, K3. And so I sum them up, K1 plus K2 plus K3, and then I divide by them. And that gives me exactly the wave function coefficient that we got by K2. Maybe more interestingly, at 4 points, the sort of unique complete tubing of this graph involves 1 circle that encircles the entire graph, and then 1 circle that encloses the left vertex and the right vertex. So the circle that encloses the entire graph pierces the 4 lines that make their way out to the boundary. Those things have energies K1, K2, K3, K4. The left vertex, let's say, is pierced by the 2 lines on the left, K1 plus K2, and also pierces this internal line, who I will assign energy S, because it's kind of like an internal exchange for energy. Okay? And then similarly for the right vertex. Sorry, I'm realizing these are like colored totally wrong. I apologize. So yeah, ignore the coloring. Sorry, I apologize for that. Okay, sorry. The red one is the black one. Sorry about that. All right, very good. Okay, so here it's quite nice because there's a single way of doing things, And similarly, it gives you the wave function as a single term expression. But of course, at some point, the party stops, if you like. And at three vertices, so this would correspond to the 5-point function, there are actually now 2 possible ways of circling the graph. And the rule is you just sum over both of them. So you see here, there are 2 possible ways of circling this graph. Sorry, it's a little hard. And so similarly here, there are sort of 2 terms. So this one, here the colors actually are correct. So here this purple rational function is associated to that purple circle over there. This orange rational function is associated to that orange circle over there. Okay. And the nice thing about this is if I hand you an arbitrarily complicated graph, you can do this procedure, generate what is the flat space wave function, and then try to integrate it to get the cosmological wave function, at least in this simple model. Okay. And it's kind of fun to do. There are you can derive nice recursion relations, things like that. Yeah, you can go home, sit in your hotel, and derive the wave function to 800 points or something, and then show me what it looks like. Okay, so we want to abstract some lessons from kind of these formulas, which now we have simple ways of generating the flat space wave function in the theory of a massless scalar. And what are the lessons that we can abstract from it? So one lesson, which I think is particularly relevant, at least in this room, is that the singularities, this is a rational function. We should be interested in where it's singular. And the singularities of this rational function have meaning. So the singularities occur precisely when some of the energies associated with these tubes vanish, right? So it's telling me that when the energies flowing out of a vertex happen to add up to 0, this object is singular. And the space-time interpretation of that is if, like, a process accidentally conserves energy. Okay, so if that happens, this thing is singular. And there's sort of one particularly interesting singularity, which is when the total energy involved in the process happens to add up to 0. And in that case, the singularity of the coefficient is just the corresponding scattering amplitude for the same process. And so there's a kind of beautiful connection between the physics of the wave function and the physics of scattering amplitudes. Okay. One thing I should mention is that here the energies are all positive, at least for real kinematics. And so in order to actually access this singularity, I need to analytically continue. And so in some sense, that's nice because we don't really like measuring infinity in the real world. So it's kind of, calming that we need to go off into the complex plane in order to make something infinite. But it also means that we can employ some of the tools of complex analysis to leverage these singularities to do interesting things. Okay, and more generally, in addition to this sort of total energy singularity, these singularities where the energy flowing into a vertex vanish are also related to scattering amplitudes and kind of lower point wave functions. So there's a sort of slightly different, maybe slightly more non-trivial version of factorization, where going to this singularity, the object does not literally split into lower point wave functions, but it splits into some kind of funny objects, which I can show you. Okay, good. All right, so this is basically everything I want to say about the flat space wave function per se, but at least in this particular model, it's like a totally, at least, again, so I'm mostly at tree level here, it's like a totally controllable object. Okay. All right, so now I want to go back to cosmology. Okay, so I told you the cosmological wave function is like an integral of the flat space wave function over its energy, roughly speaking. And so here, for example, is the cosmological wave function in this model coming from a single exchange. And so one framing of the challenge in this context is how do we do integrals like this? So it's an integral of a rational function, some kind of twist parameter. Yeah, it turns out this is a very nice integral. So okay, if you showed me this integral, I don't know, 4 years ago, 3 years ago, whatever, I wouldn't have been very happy, but now I'm very happy. This is a nice integral, okay? And I think you all know these are nice integrals, okay? But it's useful to take a step back and ask, what is the problem we're actually trying to solve, right? So what we want to know is as I change the kinematics that the correlations depend on, how does the strength of correlations actually change? And as a matter of practice, I'm typically interested in infinitesimal deformations of kinematics, okay? And so all of our physics training would tell us, right? If you're asking a question like, how does the strength of correlations change as you change the kinematics? And you can phrase that as an infinitesimal question. Sort of the right thing to do is to find the differential equation that controls this problem, and then just solve it, right? So that's sort of the morally correct way to do it. So that's good. Okay. Luckily for us, these are nice integrals, right? So the flat space wave function is a rational function with a bunch of linear factors because they're all associated to like the sums of energies inside these tubes. And so I can naturally associate the integrand to a hyperplane arrangement, okay? And I think you all know better than I do that integrals associated to hyperplane arrangements are very nice. Okay, so that's why I say this is a nice integral. These are all very simple integrals. Okay, so as an example, this two-site FRW integral that I just showed you, so it's a rational function with 3 linear factors, and then it has like kind of 2 twist parameters which are related to cosmology, so I should think of those as being singular. And so the hyperplane arrangement associated to that integral has kind of 5 singular lines, and this is the reason that I'm showing you this one is it's the only one I can draw because I'm not very good at visualizing higher dimensional stuff, but in general it'll be a hyperplane arrangement in higher dimensions. And these are precisely the singular lines associated with various kinematic factors appearing in the center. Okay. But once you have kind of this geometric picture, then you're kind of in business, because there's a whole mathematical apparatus devoted to doing integrals of this type. So the 2-sentence summary of how you do this kind of integral is you actually free your mind and consider a whole family of integrals that share the same singularities as the object that you actually care about. And you might think that that is a really bad idea because I've traded the one integral I want to do for an infinite number of integrals. But there are linear algebra saved you. So it turns out there's kind of a beautiful fact that there's actually only a finite number of linearly independent integrals. And here, it's kind of, again, amazing. It's related to the mathematics of hyperplane arrangements. But here, you kind of just look at the picture and count how many independent integrals there are. So it turns out the dimension of the sort of cohomology is the same as the number of bounded chambers of this hyperplane arrangement. So here, you draw this little picture. You say, oh, okay, there's 1, 2, 3, 4 closed regions. That tells me that any integral of this type will be disassemblable into some linear combination of 4 sort of fundamental integrals. Okay, and then once I know that, I'm guaranteed that these things solve a differential equation. I take a derivative, I just rewrite whatever I get back in this standard basis, and I just keep going, and I'm guaranteed that at some point this will close, and I'll just get some linear system of differential equations, of which the integral I care about is a part. Okay, so this is a story which I know is well known to the amplitudes community. All right, so let me show you what it looks like, at least in this context. Okay, it just is what it is. I mean, we spent a very long time playing around with this, manipulating these things, trying different bases, stuff like that. Maybe one thing I should say is a lesson that we learned, which is quite nice, is that these things, at least in our case, the bounded regions are always positive geometries, and so it's a nice thing to do to choose as our basis of integrands the canonical forms of these bounded regions. It kind of guarantees for you that the differential equations will be in epsilon form. It kind of trivializes in a certain way all of the IBPs, and so it's actually, deriving this type of equation is actually not super hard. There's like a systematic way of doing it. But the problem is once you have this equation, it's hard to like see the physics. And so we want to see some physics in this type of equation. Okay, and so for us, staring at these types of formulas was not super helpful. The thing that we found helpful was starting to draw some pictures. Okay. So of course, like I said, I showed you the differential equation for this simple exchange. You can draw me any tree graph you want, and I will go away for a little while. What I'll do is I'll write an email to Hayden Lee, and I'll say, can you plug this into Mathematica? And he'll write me back like a day later, and like, here's the differential equation. So we have sort of code that can do all of these things. But I want to be able to do this myself. I don't want to have to use Mathematica or impose on my colleagues or whatever. And so it turns out to be much more useful to represent the equations graphically. And then it turns out there's a nice underlying combinatorial structure to these differential equations. Okay. All right, so what we're going to do, so I think maybe for the amplitudes community, one reason why this is an interesting problem is this is a case where we can like completely characterize the sort of basis of functions and also the basis of like the sort of the symbol alphabet that appears in the equations. So we have a full characterization of all of the letters that appear. So let me first explain that. So the strategy is we're going to figure out what functions appear when we start differentiating things and try to understand how to organize them. We're going to try to understand what singularities appear in the system of differential equations. Then we're going to figure out what the actual differential is. Okay, so the first thing is remember that the actual integrand, the thing we're calculating, that it's very easy to figure out its singularities. It's just the flat space wave function. I told you how to get this object. I told you where all its singularities are. That's very simple. Okay, and so the integrand has some singularities at sort of complexified energy configurations. I can represent all of the singularities graphically in a simple way. They're really just literally the same tubes that I was drawing before. And for reasons that'll become kind of clear in like 10 seconds, I've chosen to mark the corresponding graph. Okay, and that's because when you actually integrate this rational function, new possible singularities appear. So this is a story that's very familiar, for example, in loop. It turns out in this case, only two new possible singularities appear, and basically they just correspond to flipping the sign of the internal energy in this exchange. And so the reason I marked this graph is I just wanted a way of encoding the sign of this internal energy. So I can also associate these letters to these particular single circlings of this graph. Okay, and the claim is that at least for this particular system of differential equations, this is all of the letters that will appear. Okay, so it turns out also, so here again, I told you there were 4 functions. It's kind of useful to give them like a graphical representation as well. And so here there are 4 functions, and it is natural to associate them to these like complete circlings or complete tubings of this marked graph. Okay. And for reasons that'll be clear in a moment, these 3 functions are kind of friends, and this function is kind of a slightly different one. And it turns out to be useful that actually you can arrange these functions in some kind of geometric picture. So this is kind of some version of like a graph associahedron, where this picture up here is representing the compatibility between these tubings, where the idea is to go to a vertex, you kind of pinch the tubing that is sitting on the line interval, okay? And then for this reason, this guy is kind of by himself, because I cannot get it by simply pinching this tubing. Okay, so this is the kind of set of letters and functions that appear in this system that I just showed you. The thing which is truly nice, and which I still do not have a totally principled understanding of, is that the differential of a function, so now I associate to each vertex and edge of this picture up here a function in the system. And the thing which is really interesting is that the differential of a function is actually local in this geometric space. So if I take a derivative of this function, represented by this tubing, I get back the same function and also the function associated to the edge related to it. And the letters that appear multiplying these functions are related to these vertices and edges. Okay, so there's some sense in which, so if I showed you a more complicated example which has volumes and stuff, you start on a vertex and you march your way to edges, volumes, etc. Okay. And so here I'm just translating for you the differential of this function on the left vertex back into this language. And you see you only get the same function and the one associated to the edge, and the letters that appear are the ones associated to that function that I started. Okay, so here in the picture, you should read these filled in blobs as being the associated letters. I actually should have deleted this left tube. It doesn't play any role. Okay, and so in our paper, we sort of called this like a kinematic flow, because it feels like you've traded time evolution for now some flow in the space of kinematic variables where you're moving through some space of functions. Okay, so let me try to insert a small amount of physics. So by doing this, I just gave you like a totally combinatorial prescription for deriving this differential equation, but you'll find that there's actually some interesting physics. So the wave function, the actual object I care about, is some linear combination of these basis integrals. And you might expect, so it's part of a 4x4 system, so it for sure satisfies a fourth order homogeneous equation just by continually taking derivatives. But you might think, well, you might be interested in whether this thing satisfies a lower order equation. Actually, it accidentally does. So there's a small mystery here, or like a small accident here, but it gets more impressive as you go to more complicated graphs, that the actual physical wave function satisfies a lower order differential equation, right? And the physical interpretation of this equation is that it's the sort of manifestation in this language of the bulk fact that it was built using a causal Green's function. So if you act with the box operator, you actually collapse the exchange, right? And so that's literally what this equation is. This is some differential operator acting on the wave function, turns it into something with a simpler analytic structure. Okay, so to me this is kind of interesting because I did start with Feynman diagrams, but I sort of didn't have to. And so this is some way of, some interesting feature of the differential equations comes out from some other point of view. Okay, so here I've just showed you some of the equations for the simplest single exchange, but one can do a similar thing for any graph. So for example, for this double exchange graph, the first thing I do is I mark the internal lines, and then I enumerate all the possible letters that can appear in the system. In this case, there are 13 possible singularities that can appear in integrated functions. Here they are associated to two things. It's not super important. If you're interested in kind of the asymptotic growth, the number of letters kind of grows polynomial in the size of the graph. The next thing I should do is I should enumerate all the functions. So here, this is actually only a piece of all of the functions in the double exchange case. This is sort of the analog of the interval that I showed you. And this thing is now, again, reflecting the compatibility of various of the functions that appear in the basis. And the full basis in this case has 4 to the number of internal edges functions. So it kind of grows exponentially as the graph gets bigger. Okay. Here, similarly, there's a nice story where if you start taking differentials of the functions associated to edges or faces, there's kind of a moving around locally in this geometry. Okay. So at least at tree level and even, well, I would say even at loops for the part of the integral that corresponds to integrating over time, we understand what to do. There's still a challenge to actually do the loop momentum integrals because they kind of no longer live in this hyperplane world, and so they're hard. Okay, so let me, in the last couple minutes, just give some outlook. Okay, so to me, there's one practical thing, which is we want to do calculations that we can compare to data and things like that. But from a more philosophical viewpoint, one of the things that's interesting to me is that even though I started with Feynman diagrams, you might have said that's a bit in tension with this philosophy that we want to get rid of time evolution, do some bootstrap kind of thing, stuff like that. So, you could say those words, but then the second you write down a Feynman diagram, it's you feel a little bit less principled. But an interesting thing is that at the end, I sort of didn't need to do that. I could have started with some roughly combinatorial rules. I could have said, okay, I live in the space of kinematics. What can I do if you give me a kinematic object? I can triangulate it. Triangulating this kinematic object is naturally associated to a trivalent graph. That graph, a natural thing to do is to associate variables to its edges and vertices. It's again natural to tube this graph and see what geometric structures appear. Doing that, I would see that I can associate letters and functions to this graph. And then if you have some sort of principled reason for why moving around in this graph with some set of rules, which is like a differential, you would see all of the structure of these cosmological wave functions appear from kind of combinatorial origins, where here the output of bulk locality, time evolution, things like that would truly be an output. Okay. If I was a little bit more brave, well, probably a lot bit more brave, I would have tried to tell the talk that way or frame the talk that way. We made an attempt of doing this in this paper, actually. We tried to frame things in that language. And it's kind of fun to try to do, because you try to see if there's a natural place where you start from just kinematics and get out something approximating time evolution. And so from this perspective of bootstrap, like living on the boundary, holography, whatever, maybe this is an interesting setting to start to think about these kinds of things. A more pragmatic thing that I will mention is, so here this was all in the context of some simple toy model. You might be interested in like computing things people care about for phenomenology. Turns out that integrals of massive fields in exact de Sitter space share many of the features that I was telling you about, so that you end up wanting to do integrals like this. These are, again, nice integrals. They're not quite as nice as the ones that I showed you, but they're not too bad. So there are many similar features, but some new interesting structures. And I think maybe just a slightly more philosophical point about the connection between our communities is that I think we're still at the beginning stages of finding sort of the nice, non-trivial overlaps between the interests of the amplitudes community and cosmologists. But so far the discussions have been very fruitful, I think. And I think there are many more non-trivial overlaps to explore. So for example, things that we're interested in understanding in cosmology are things like loops, dispersion relations, understanding like large multiplicity in special theories, things like GR, Yang-Mills, nonlinear signal model. And we're still kind of at the beginning stages of understanding all of these things. And so I anticipate that talking to you all will be a useful thing. And I'm looking forward to chatting more on this. Okay, so let me conclude. Oh, I guess my last slide. Okay. Okay, so hopefully I've convinced you, well, me and Enrico together, convinced you that cosmological correlations are interesting because they give us a glimpse of the universe in its infancy. And from the perspective of this meeting, they're an interface between gravity and quantum field theory. So they really are, in a sense, like, you know, a manifestation of QCD meets gravity. The concrete thing I told you about is that cosmological correlators have interesting differential equations, which have a nice mathematical structure. And in particular, the nice mathematical structure lets you get quite far. And I think it's really just the tip of the iceberg as far as connections between cosmology and scattering. Okay, I'll stop there.
Thanks for the nice talk, Austin. I kind of want to connect a bit with what Enrico was saying in his talk about, you know, how we really don't know what we should expect for quantum field theory on a cosmological background. What is the space of theories? How do we organize it? Just a very nice discussion of how we compute wave function coefficients, tree level. There's a nice structure there, but do you think that this can give us a picture on how to organize field theory more generally? What is the space of field theories that even makes sense on cosmology beyond this structure?
Yeah, so that a bit goes to maybe this slide, right? So to me, okay, maybe there are, let's say there are three kind of conceptual ways that you might try to carve out theory space. Maybe there are more, but this is the way I would organize my thinking. One is just understanding sort of what theories are sort of consistent, like roughly kinematically, let's say, in the sense that you might wonder, like in flat space, you might have thought that the menu of things is like, give me any mass, any spin, there must be a theory which is consistent. But we know, for example, there's no massless spin 14 theory, something like that, right? So that's already some set of constraints. And to be honest, we don't have the most principled, pure version of those constraints at cosmology, things just coming from consistent interactions involving massless particles. So for example, there are these questions about partially massless theories, things like that. So that's one avenue. And that avenue, I think, is well studied using these kind of on-shell observable kind of tools. Another one is this thing written on the slide. So another version of what is allowed is like what effective field theories actually admit ultraviolet completions, right? And there, I think, in principle, that requires like non-perturbative, at least. You have to dream a bit non-perturbatively and make assumptions. But at least historically, the way that people knew what sort of non-perturbative assumptions to make about the S matrix was by doing some calculations, seeing what the analytic structure was, and trying to prove that was the case. So that, I think, is another avenue where perturbation theory can be informative. Then there's sort of a totally non-perturbative way of proceeding, where you try to set up some bootstrap kind of thing. That it's less obvious to me how perturbation theory will inform, but I think that is complementary to the perturbative approach. I don't know if you find that any of those answers satisfying. But...
Other questions for Austin? Okay, if not, thanks all the speakers in the morning again. So the lunch will be served outside, and just to remind you, you can either have it here.